Now, if this problem were to be solved on 2 dimensions, this is a single dimension, single facility location problem. What if this problem was to be solved on 2 dimensions, right? Okay, so this approach is called cross median approach, right? So what does the result say? Result says that the vendor shop should be located at the median with respect to the demand density. Median, right? Median meaning, what is the definition of median? You arrange the data and what is median? Median is such that 50% of the data lies here, 50% of the data lies here, and the middle value is the median value, which is exactly what we got, right? So we are saying that this weight should be same as this weight. If there are 100 customers here, there should be 100 customers here. So totally there are 100 and 100 to 100 customers, and you located the facility right in the middle. Therefore, you are locating at the median, and therefore this approach is called cross median approach. Okay, now if we were to split this or if we were to extend this idea to 2-dimensional problem, right? Now I am not talking about a single beach which does not have y-axis, right? Here we said that there is no y-axis because the beach, the width of the beach is fairly small for us to consider anything, right? What if there was a y-axis? What if it mattered how much are the customers traveling even on the y-axis? Now, let us take both the distance measures, Euclidean distance measure and Metropolitan distance measure. Let us first of all take Metropolitan distance measure. How would the problem be solved? Metropolitan distance measure would say there are n zones. The distance travelled in the x-axis is xi minus xs, where xs is the location of the facility. Xi, yi are the coordinates of the zones, right? Let us call them zones. Right, and this is also zone. So Wi continues to be the demand density or the weight in the ith zone. If it was a metropolitan distance measure, remember what was metropolitan distance measure? Metropolitan distance measure was distances are measured, amount of travel in the horizontal direction, amount of travel in the vertical direction. Right, that is the total distance travelled according to Euclidean distance. According to Metropolitan distance measure. Okay, so the total distance travelled in the x-axis, which is this guy. Total distance travelled in the y-axis, which is this guy. Multiply that with the corresponding weight. Right, multiply that with the corresponding weight, and you are still minimizing the total weighted distance travelled by the consumers, which is the same objective that we had earlier. Just that this objective was solved on a single dimension. Now we are trying to solve it on 2 dimensions. Right, xi, yi are the locations, the center of the locations of the zones, and xs, ys are the potential locations of the facility. Xs, ys are our decision variables. In this optimization problem, xs, ys is the that's the location of the facility. Unfortunately, we don't know the value of xs, ys. I know the value of xi, yi because I know the zones. I know wi, so wi is known. I don't know xs and ys. How would you solve this problem? Right? Since x and y coordinates seem to be independent of each other, we can actually solve these problems as 2 independent problems. Right? Why can't I solve it like this? I will solve the weighted distance minimization on the x-axis, weighted distance minimization on the y-axis. Nothing stops me from separating the problems into two sub-problems. And I should do that because that makes the problem easier. Right? So the optimal location of the service facility will be xs at the median of wi in the x direction, and ys will be the median value of wi in the y direction. Right? Earlier that's what we said. So this was our cross median solution. This was only in 1 dimension, which was only the xi dimension. Now I will solve an independent problem in the y dimension and essentially do the same. Right? Here we said this is weight 1, weight 2, weight 3, weight 4, weight 5, weight 6, and my facility was such that the total weight on the left should be same as total weight on the right, which is the cross median in terms of x direction, which will be my xs. So this will be my xs. This will be my xs. Now I will solve another problem on the y dimension, where y1, y2, y3, y4, y5, y7, y6, y7, they are all the weights in the y axis, and I will locate my facility at ys in such that the total weight on the top is same as total weight on the bottom of this line, right? So I can definitely separate the two problems into two sub-problems, this problem into two sub-problems, right? And solve this as a cross-median solution in 2 dimensions. Now, because I may not exactly match the location on the x-axis with a corresponding single point on the y-axis, I may get a region or I may get a point as an optimal location. What do I mean by that? Let me clarify from an example. Okay, let me take a very smallish example. Let us say that this is a 2-dimensional graph and I have 4 demand locations. Demand location 1, 2 and 3 and 4. The coordinates are given, right? Coordinates are given. So for the zone 1, location is 1 and 2. So this is your 1 and 2, 1 in the x-axis and this on the y-axis. Service zone 2 there are some customers sitting and the location is 2 and 3, right? 2 and 3. Now the W in the brackets are the weights, right? Demand density. You can think of that as 7,000 customers in zone 1, 1,000 customers in zone 2, 3,000 customers in zone 3, 5,000 customers in zone 4, right? And the location of each of the zones is known, right? What I don't know, I don't know where should the service facility be, right? Where should this XS be? XS, YS, where should that be? Now let us collapse all of this in the x-axis and solve the problem for x-axis, right? Because we said we can actually separate the two problems and solve one problem for each axis separately, independently of each other. So let us collapse all these weights. Let us collapse all these weights on the x-axis and solve the problem as if we are trying to solve a single dimension problem that we have already solved. What would the cross-median approach say? Cross-median approach would say that the facility should be located at the median. Now what is the median? Let us calculate the median. So here the demand is 7, 1, 3 and 5. 7, 1, 3 and 5. Divide that by 2. You get a median weight of 8. Median weight of 8. Now where should the facility be located? The facility should be located such that the weight on the left of the facility should be same as the weight on the right of the facility. And what is that median? Median is at 8. So let us move from left to right. 7 plus 1, 8. Which means I can actually locate the facility right here, right next to 2, because my 8 is reached. 8 is my median. Cross median approach would say I should locate my facility at the median. So my median is reached at 2. On the x-axis, my median is reached at 2. My median is reached at 2 and therefore I can locate the facility at 2. Right? What happens if I go from right to left? 5 plus 3 is 8 and therefore it allows me to locate the facility at 3. Exactly at 3. Exactly at 3. And because at 3, my median weight has reached. Right? Want to show this? Ordering from west to east, right? From west to east, going from left to right. Demand location 1, the coordinate is 1. Demand location 2, the coordinates are 2. And the weight is 7 and 7 plus 1, 8. 8 is reached and therefore the facility should be located at 2. Now going from east to west, which is from right to left. Demand location 4, coordinate is 4. Demand location 3, the coordinates are 3. But here, by the time I hit 3, my median is reached. So, if you go from west to east, the optimal location is 2. If you go from east to west, the optimal location is 3. So, there are 2 ideal locations. And I would argue that not only 2 is ideal location, 3 is ideal location and therefore any point between 2 and 3 would also be an ideal location. So, this is what I meant by optimal location resulting in a range, in a line, in a region. So here it says I can locate the facility anywhere between 2 and 3 on the x-axis. Now let us solve the same problem on the y-axis, right? Let us solve the same problem on the y-axis. So for that, let me remove some clutter. Let me remove this. Let me remove all this. Okay. and let me collapse all of these on the y-axis now, right? Location 4 collapsing on the y-axis, collapsing on the y-axis, collapsing on the y-axis, collapsing on the y-axis. Everything is collapsed, and these are the weights on the y-axis. These are the weights on the y-axis. Now let us solve the problem for the y-coordinate independently of the problem that we have solved for the x-coordinate. So let us go from top to bottom. The weight is 3 plus 1 4. I have still not hit the median. Median is 8. 3 plus 1 4. I have not hit the median. 4 plus 7 is 11. That's it. I have crossed the median, and therefore my facility should be located at 2. If I go from top to bottom, at 2 my median is reached. At 2 my median is reached. I could not have located the facility before this, right? I could not have located the facility here. I could not have located the facility here because my median had not reached by then. Median was 8 and I had reached 3 plus 4. Weight was only 4. Median is 8. Could not have located the facility before this. So this is my optimal location recommended from going from top to bottom. What if I go from bottom to top? First location that I will hit is 1, which is weight of 5. My median is not reached. I cannot locate the facility. Cannot locate, cannot locate, cannot locate, cannot locate, cannot locate, cannot locate. And suddenly I hit this y equal to 2. That coordinate, the weight is 7. And now 5 plus 7 is 12. I have crossed the median, and therefore going from bottom to top also recommends that I locate the facility on the y-axis at y equal to 2. At y equal to 2. Hope that is understood. So on the y-axis, I actually get a unique location. Y equal to 2 is the unique location going from bottom to top or from top to bottom, right? That's a unique location, which is something that I did not get when I solved the problem on the x-axis. Okay, so just to tell you that this is true. So going from south to north, going from bottom to top, 2 becomes the location because my median is reached. Going from north to south, again point number 2 becomes the location. Point number 2 becomes the location, right? Point number 2 becomes the location because my median is reached. So y equal to 2, y equal to 2 here, y equal to 2 here also. So I get a unique solution, right? I get a unique solution. How do I plot it back on the coordinate axis that I had? Let me erase some clutter. Let me remove all of this. So let me write down the recommendations now. What was the recommendation on the y-axis? Recommendation on the y-axis was this single location y equal to 2. Y equal to 2 was a single recommendation. Y equal to 2 was a single recommendation. X-axis, the recommendation was anywhere between 2 and 3. So between 2 and 3. Right, so I will extend this. And where should my facility be located? If these are the locations, where my consumers are sitting, the cross median approach says that I can locate the facility anywhere in this line, anywhere on this line, anywhere where the y is 2, x is between 2 and 3, including 2 and 3. So anywhere on this line, including x equal to 2 and x equal to 3, is the optimal location based on the cross median approach. Based on the cross median approach. Okay. So this is locating a single facility on multiple, actually 2 dimensions, on 2 dimensions. But here, because I considered metropolitan distance measure, I was able to very easily separate the problems on the x-axis with the problem on the y-axis. I was very easily able to do that. Doesn't matter, I have still solved a single facility location problem for a metropolitan distance measure, and here I did not get a single location, I actually got multiple options. Anywhere on this line, I can locate my facility. I can locate my single facility. Hope this is clear to you, right? Hope there are no questions here. But this is how you solve a single facility location problem on a metropolitan distance measure. What if my distance measure was not metropolitan, but the distance measure was Euclidean, right? How do I measure distances using Euclidean measure? the square root formula. This is how I measure distances using Euclidean distance measure. So for my let us solve the same problem. We had hypothetically considered this problem, right? 4 doesn't matter, 4, 5 doesn't matter, but so distances now will be measured differently. So here my xs and ys are arbitrary points. I don't know what the locations are, but now I am measuring a Euclidean distance measure. So I will directly draw a line between the facility and the location, demand location, and this is my D3 because this is the distance between service facility and demand location 3. This is D4 because this is between demand location 4 and service facility. This is D2, this is D1, right? And obviously I am trying to minimize the total distance that all my consumers have to travel, weighted distance, total weighted distance. So how will that formulation look like for the Euclidean distance measure? Right, so I actually got a non-unique solution 2, 2, 3, 2, 2, 2, 3, 2, just to confirm, right? This location is 2 and 2, this location is 3 and 2, and therefore anything in between also is an optimal solution. That was for the cross median approach. For the Euclidean distance measure, right? This is the distance formula. Right? Xi minus xs whole squared, yi minus ys whole squared, and the square root of that. Weighted distance, therefore wi, and summation of all such distances is the total weighted distance measure. And I want to obviously minimize this distance because this is what my consumers are actually traveling. This problem is slightly more complicated. First of all, I cannot separate the x problem from the y problem. I have to solve them together. Therefore, when I am trying to solve xs, remember what are the decision variables here? The decision variables are xs and ys. Those are the coordinates of the service facility that I do not know about. Where is this xs and ys? I don't know. Whereas x1, y1, x2, y2, x3, y3, x4, y4, I know. wi, w1, w2, w3, w4 also I know. So this wi's are known, xi is known, yi is known, xs is not known, ys is not known. So this problem is complicated not only because I cannot separate the x problem from the y problem. This problem is also complicated because it is a non-linear optimization problem. Non-linear because we are talking about the quadratic function, square root function, and so on, right? So it's a non-linear optimization problem. If you were to solve this problem, you get the optimal location. Oh, I'm sorry. This should be xs and ys. I have corrected the typo, and now I am saying the optimal location in the x direction turns out to be this equation, and the optimal y coordinate turns out to be this equation. So if you can notice, yi xi divided by dis divided by wi divided by dis, and what is dis? Dis is this distance. Similarly, there is a dis. Dis is the distance between the demand location I and the service facility S, right? Dis. Notice that when you are trying to solve xs, you will need ys because you will need dis. Similarly, when you are solving yis, you will need dis, where dis will also have xs. So the problem is complicated not only because it's non-linear, but you cannot even solve for xs without solving for ys. You cannot solve for ys without solving for xs. So those also have to be solved simultaneously. So not only I was able to not separate the x problem with y problem, even when I got the optimal solution, even now I cannot separate the two. I have to solve xs and ys together. It's slightly more complicated, and therefore it has to become an iterative process. Right? Understood the idea? Idea is still the same. I have not changed the objective function. Objective function is still minimization of the total meaning summation, some total weighted distance, right? Minimization of the total weighted distance, right? You can actually see English getting converted into mathematics sequentially. Minimization of the total weighted distance. That objective is still the same. That was the same objective in the Metropolitan distance measure, but here the solution gets much more complicated because of the non-linearities. Also, you will realize that there is going to be a single value of xs and single value of ys Unlike my metropolitan distance measure where I got two solutions and both of them were optimal, actually anything in between is also optimal. Here I am going to always get a single value. Xs is going to be a single value, ys is going to be a single value. Okay. So how do I solve this? I told you this is difficult because to solve xs I need ys. To solve ys I need xs. I have to solve simultaneously. So we have to use some numerical algorithms, right? One way to solve is to use what are called as center of gravity method, right? Center of gravity method. So what is center of gravity? Go back, right? Go back to this problem. Center of gravity. What is generally center of gravity? Think about a waiter holding a tray. There is a cup here and there is a bowl here. Then there is another bowl here, there is another bowl here. These have weights W1, W2, W3, W4, and the service person in the restaurant is trying to hold the tray right at the middle. Imagine you hold the tray with a single finger. We do that at home sometimes and miserably fail. At least I fail miserably. So what is that single location where the complete tray balances? I can honestly tell you that I have tried and failed. What is that single location? That single location is the center of gravity, right? So what is that center of gravity solution? Center of gravity solution will tell you that x coordinate will be wi into xi divided by wi. Y coordinate will be wi into yi divided by total of wi. So wi xi known, wi yi known, and therefore center of gravity solution can be easily calculated once you know the data, right? If you know the data, you know the data. The coordinates are known, so xi, yi are known, wi's are known, and therefore you should be able to calculate the center of gravity. However, you have to realize that center of gravity actually does not minimize the total weighted distance. It does not. But it's a good enough starting point, right? So center of gravity solution is what we call as a heuristic solution. Remember last time we spoke about heuristic solution. Most of these optimization problems, when they get too hard, we have to satisfy ourselves with only getting a good enough solution, not an optimal solution. Center of gravity solution is one of those solutions. Good enough solution. It's a good solution. Easily obtainable, right? Not a bad solution, so to say. But it is non-optimal. Okay. It does not minimize the total weighted distance. So what we can do is, we can employ some kind of a numerical algorithm to actually solve this guy, and we can use center of gravity solution as the starting point of that numerical algorithm. That should be possible. Okay, that should be possible. So center of gravity solution can be used as a starting point of our numerical solution, because that actual problem is a much tedious problem to solve. Is a much more tedious problem to solve. Okay, so that is how you would solve for a single facility location problem using a Euclidean distance measure. We have seen metropolitan distance measure, it results in a cross median approach. Now this is a Euclidean distance measure. What is the differentiating feature? Euclidean distance measure will always result in a single point. Optimal location will always be a single point, whereas in the metropolitan distance measure you may get a region. However, in the Euclidean distance measure, the optimal solution will rarely match the center of gravity solution. Center of gravity solution is most of the times not optimal solution. Okay, so that is how you would solve for a single facility location problem. So we have covered both the distance measures. Even though we have considered only a single objective, minimization of total weighted distance, you can think of the method is not going to be different. You can think of maximizing the objective, maximizing not the distance probably, maximizing the benefit that the consumers get, and then you will have to have mathematical formulation for what is a benefit for the consumer. What if I want to maximize my profits, and therefore I want to maximize the objective as maximization of my profits? That can also be done. So we have not looked at different objectives, but we have looked at different measures of distances. Okay, so that is about a single facility location problem, and now the next thing to be done is to look at multiple facility location problem.